Beneath the ocean's surface, life seems familiar. Colorful fish, coral gardens, sunlight shimmering down. But the deeper you go, the stranger and more unsettling the inhabitants become. Bioluminescent flashes and bizarre shapes hint at secrets where sunlight vanishes, pressure crushes, and evolution breeds monsters. What forces sculpt creatures so alien they unsettle even seasoned scientists? This is just the beginning of a descent, where every meter reveals something more haunting, and the question is not just what is down there, but why it had to become so strange. At the ocean's surface, sunlight pours through clear water, fueling a world that feels almost familiar. Here, in the upper 200 meters, known as the epipelagic zone, vision rules. Schools of tuna flash silver as they dart through open blue. Coral reefs host a kaleidoscope of fish, their colors vivid in the sun's rays. Jellyfish drift by, their bodies nearly invisible except for the gentle pulse of their bells. This sunlit layer is where most ocean life begins and ends, where photosynthesis supports a bustling food web and oxygen levels remain high. But even in these welcoming shallows, the rules of the deep begin to take hold. For every 10 meters descended, pressure increases by 1 atmosphere. At 100 meters, a diver already feels the squeeze of 10 times the pressure at sea level. Most surface creatures are built for this gentle gradient, their bodies adapted to the light, warmth, and abundance of food. Familiar predators like dolphins and barracuda patrol these waters, hunting in packs or with bursts of speed. Plankton blooms feed everything from tiny anchovies to massive whales. Yet as sunlight fades with depth, a sharp boundary forms. Below 200 meters, the sea darkens rapidly. The pressure mounts and temperatures start to drop. Scientists preparing for deep sea dives check the hulls of their submersibles and the seals on their cameras, knowing that every meter deeper brings new challenges. The surface world offers a baseline, life shaped by light, color, and abundance. Soon, those certainties will vanish, replaced by adaptations that defy expectations. At 200 meters, sunlight drops to a faint blue haze. This is the mesopelagic, the twilight zone, where vision begins to fail and survival depends on new tricks. Lanternfish drift in slow-moving schools, their bellies lined with rows of glowing dots called photophores. These organs produce light through a chemical reaction, bioluminescence, turning the fish into living lanterns. But the glow is not a beacon. It is a disguise. Lanternfish use counter-illumination, matching the faint light from above to erase their own shadows. Predators below see nothing but empty water. Studies show that this camouflage can cut detection by over 90%, saving precious energy that would be wasted on frantic escapes. Nearby, hatchetfish float with bodies so thin they almost disappear. Their large tubular eyes point upward, tuned to catch the last hints of daylight or the flash of prey. Some species are nearly transparent, their organs tucked behind mirrored scales that scatter any stray light. In this world, being seen is dangerous, so every adaptation is a trade-off between hiding and hunting. Marine biologist Edith Witter describes the twilight zone as a place where bioluminescence is cheap signaling in darkness. A tiny flash means dinner. Here, more than 3/4 of all known bioluminescent species live. From jellies that pulse with blue-green light to shrimp that squirt glowing clouds to escape. Each flash, each shimmer, is a survival tactic in a realm where food is scarce and the line between predator and prey blurs with every pulse of light. As the last traces of daylight vanish, anticipation builds. The ocean is about to plunge into total darkness, where even stranger adaptations wait. At depths beyond 1,000 meters, the ocean enters a realm of constant darkness and crushing pressure. Here, food arrives only in rare pulses, tiny flakes of organic matter drifting down from above, or the occasional carcass. sinking from the world of light. In this midnight zone, survival demands anatomical extremes. The fangtooth, Enoplogaster cornuta, is a masterclass in this logic. Its head is oversized for its body, and its teeth, the largest in proportion to body size of any fish, curve inward like ivory daggers. These teeth are so long that the fangtooth's skull has special sockets to accommodate them when the mouth closes. With vision nearly useless, it relies on a keen sense of smell and the ability to snap at anything that brushes past. Each encounter is a gamble. Missed meals may mean months without food, so nothing is left to chance. Nearby, the gulper eel, Europharynx peleconoides, waits in near motionless suspension. The gulper eel's jaw can unhinge and expand to engulf prey half its own size or larger, forming a balloon-like pouch. This adaptation isn't about gluttony. It is a response to scarcity. When a meal finally appears, the gulper eel must seize the opportunity, swallowing as much as possible in a single gulp. Gut content studies show that a single large catch can sustain these eels for weeks or even months. The energy budget is unforgiving. Slow metabolism, gelatinous tissues, and opportunistic feeding all serve to stretch each rare calorie as far as possible. In this world, grotesque forms are not accidents. They are the blueprints for survival when the next meal is never guaranteed. At nearly 900 meters, a remotely operated vehicle drifts in the black, guided only by a thread of fiber optic cable and the faint glow of its red LED lights. These lights, invisible to most deep-sea animals, let the ROV slip through the water without startling its quarry. Its cameras, built around ultra-sensitive sensors, pick up even the weakest shimmer, a flash of bioluminescence, a shadow against the endless dark. Then, without warning, a shape emerges. Long arms, pale and ghost-like, unfurl from behind a curtain of marine snow. For a moment, the control room falls silent. The pilot's voice cracks through the intercom. "We have something big, moving fast." The monitors fill with the image of a giant squid, its eyes reflecting the ROV's faint red light. The animal hovers, tentacles poised, before vanishing into darkness with a single slow pulse. It is the first time anyone has seen this legendary creature alive at such depth, behaving as it does in its own world. The ROV's non-invasive lighting and pressure-resistant housing make this possible, capturing a living giant where trawls would only bring up mangled remains. Each detail is recorded in high definition: the ripple of muscle, the flicker of chromatophores, the glint of a photophore along a tentacle. A pilot from the Monterey Bay Aquarium Research Institute later recalls, "For a second, nobody breathed. It was like staring at something from another planet." Technology turns the abstract horror of deep-sea monsters into a lived, undeniable reality, one that leaves even seasoned researchers shaken and eager for answers. At depths below 4,000 meters, life faces pressures 600 times greater than at the surface. Here, the rules of biology are rewritten at the molecular level. Anglerfish drift through this abyss. Their bodies are soft and gelatinous, built to resist crushing forces that would shatter bones. The giant amphipod Alicella gigantea grows to nearly 30 centimeters, almost 10 times the size of its shallow water relatives. Gigantism is not a quirk, but a survival strategy, allowing these scavengers to store energy from rare feasts. Deep-sea creatures rely on a molecule called trimethylamine N-oxide, known as TMAO, which accumulates in their tissues. TMAO acts as a stabilizer, keeping proteins from collapsing under extreme pressure. The deeper the animal lives, the higher its TMAO concentration. That chemical gradient marks the boundary between possible and impossible life. These adaptations create forms that seem alien, Yet every feature is a solution to the relentless demands of the abyss. Human eyes and instincts are tuned for the ordinary, faces, symmetry, and movement that fit familiar patterns. The deep sea breaks those rules at every turn. Sharp teeth, glowing eyes, and bodies that bend or balloon in unpredictable ways set off alarms in the brain's amygdala, the ancient center for fear and threat detection. When a creature's features do not match anything from daily life, the mind fills in the blanks with caution, even dread. Neuroscientists studying these reactions point to the uncanny valley effect. The more a form strays from what we know, the more unsettling it feels. Less than 5% of the ocean floor has been mapped in detail. So when researchers encounter something truly alien, the response is primal. One neuroscientist says, "Our brains evolved to fear what we can't predict, and the deep sea is full of surprises." Over 80% of our ocean remains unexplored. As technology pushes deeper, each discovery challenges what we know about life's boundaries. The unknown is not empty. It teems with forms shaped by extremes. In a world of shrinking frontiers, the ocean still holds mysteries that force us to rethink what is possible.